All right. Can you see my slides?
Yes,
Perfect.
we can. Yeah.
Okay. And are we ready to start?
Yes, I will just introduce you. So,
Okay.
I guess Mario you could have talked about many proof assistants, but you chose, or maybe we chose, Metamath, and well, I'm curious about what lessons we can learn from that. So please go ahead.
Yes. So, um, yeah. So the title of the talk is Lessons from Metamath, and the idea is that Metamath has it's an unusual system in many ways, and there are many things that we can learn from Metamath and the way it does things. Now, I want to preface this by saying that this is in memory of Norman McGill. He's the creator of the Metamath language, a longtime friend, and he passed away last year. Um, and without him, really none of this would have happened. So I'm very grateful to him. Um, so Metamath is, it's a computer language for writing mathematical proofs. It's a proof assistant. Well, it is a computer language for writing mathematical proofs, which is to say a verification language. But the term can also be applied to the program metamath.exe, which is a proof assistant for verifying and writing proofs in the Metamath language. And you could also extend it to the library of completed proofs in a wide variety of axiomatic systems. The largest one is set.mm, which just breached 40,000 proofs of consequences of ZFC. And this covers a whole bunch of different areas of mathematics, including 74 of Freyk-Dijk's list, which puts it up there with some of the larger theorem provers. There are other databases as well. iset.mm is deriving proofs in intuitionistic ZF set theory. NF is doing Quine's new foundations set theory, and QL.mm is doing quantum logic, which I don't know that much about, but apparently Norman McGill thought it was an interesting logic to prove theorems about, and he did quite a bit. And there are other databases like HOL.mm, dependent type theory, P&O arithmetic, and even Hofstadter's MIU system. So this is just to say that Metamath supports a very wide variety of axiomatic systems, including, strange logics that maybe you don't know that much about. If you open up set.mm, you're going to see something that looks something like this, and you can see over on the left that the line numbers are going into the 5 digits. So set.mm is actually one file for historical reasons, and you can see that it has these are comments on each theorem, the names of the theorems, the statement of the theorem, and this block here is basically a compressed proof object of the theorem's proof. But usually you aren't going to be working with that. Instead, as an author, you're probably going to be working with a tool like this. This is MMJ2. This is a proof assistant for Metamath, and here we're using it to so the proof assistant actually generated this proof here of so there's a button that you can press and say, hey, give me a proof of 95 plus 1 equals 96, and then it spits this out. The main way that you're probably going to see Metamath as an external user is something like this. So this is the Metamath Proof Explorer, or the HTML web pages for Metamath. And you can see in these pages all of the theorems, their statements, their proofs, and the axioms that were used in the proof of the theorem. So my goal is really not to convince you to use Metamath. My goal is instead to have you think about what Metamath does differently and how you can incorporate these ideas in your favorite theorem prover. Also, I've been working on a verification system called Metamath 0, which borrows heavily from a lot of these ideas. So I'm going to tell you a little bit about how I made use of this stuff in the design of MM0. Okay, so three major components show up when you look at, what makes MetaMath different. And I summarize them here. One is that we want to separate proof authoring from proof checking as things that we want to do. Another is to have a simple spec for a logical core. And then there's several sort of logical innovations involved in how MetaMath operates, like the use of direct substitution instead of the first order logic proper substitution. So I'll talk about these one at a time. So interactive theorem provers fundamentally need to support two basic activities. One is writing proofs, or authoring proofs, and the other is checking proofs. And the design criteria for these are completely different. Writing happens once. You write the theorem and then you've proved the theorem. I mean, there is maintenance that can happen, but for the most part, writing happens once or just a few times, whereas checking happens many times. It'll usually happen, every time, any time there's a change, it shows up in CI. Anytime someone downloads the thing, they're probably going to want to run, to be able to check it just so that they can make use of it, depending on to what degree that needs to be done. Writing often involves human interaction and creativity. So writing really needs a proof assistant, but proof checking needs a kernel. And these are at odds. A good proof assistant is big and complex because the user experience is driven, those human-computer interaction things, they're driven by features, and features take up space in the code. Whereas a good kernel is small because in order for it to be trustworthy, you want to know that there are no bugs or as few bugs as you can. And the best way to make sure that there are no bugs, besides proving it correct, is having fewer lines of code to have bugs in. And ideally, it should also be fast and not resource intensive because of the whole CI thing. The main, not the only, but the main way that MetaMath does this separation is by storing proofs, not proof scripts. And so I'm recalling here that picture of set.mm. You look at this and you wonder, where are my tactics? Well, this isn't a thing that tells you how to make the proof. This is the proof. This is actually the sequence of steps that were generated. And as a result, checking this is extremely fast. So the classic verifier, the original metamath.exe, can check set.mm. This is a 42 megabyte text file, and this can be checked in 8 seconds. There's a more optimized metamath verifier which can do the same thing in just under a second. So this, I would say that the main reason why this is possible, there are a couple of reasons, but the main reason why this is possible is because what's actually being stored, what's actually being checked in to the repository is actually these compiled proof objects. So I want to highlight that as sort of one of the takeaways here is that really we should try to cache compiled proof objects. And depending on the system, this can be more or less difficult. So Lean has these OLean files and Cuck has VO files, but they're generally not used for fine-grained caching, and they usually aren't checked in either. Like caching at the level of an individual theorem is not something that you can easily do with these methods. And Hull, Light, and Isabel are in a really bad position here because proofs in LCF are basically, by definition, you have to run a program, and the program goes to the kernel, and the kernel checks by virtue of running. So you can't extract the running from the checking. They're really the same activity. And if the running involves running a large tactic that's doing a search or something like this, then you have to pay for that every time. As of yet, MM0 doesn't really do anything special for fine-grained caching, but it can import precompiled files, and there is the idea that the precompiled files can potentially come from multiple different sources, not necessarily just the proof assistant. So you can sort of play with imports that way. Another thing is that you should have a sort of verifier-friendly format that is fast to check. This is useful for CI because you can run CI on this format and have additional assurance. It's useful for proof translations. You can make use of this to translate your proofs into a different proof assistant or another language. And it's useful for auditing. If you can extract that format into a separate thing, then you can understand that separate thing without having to understand the entirety of the proof assistant. So that's very helpful. And you should have a small trusted kernel. Most of the systems that I'm talking about here do have a small-ish trusted kernel. But if you need to have a PhD to understand the code of the kernel, then it's not small enough. And external kernels are better if they're intrinsically connected to the proof assistant itself. Then it's difficult to argue for the correctness of the kernel without the rest of the stuff. And it also makes it easier to use with the external, like proof translations and auditing and those other things.
Maria, could I interrupt with a quick question on that?
Good, yes.
So one of the reasons that you might argue against this sort of separation of proof script from proof is robustness, right? If you want to go back and refactor your library, but your library is, I mean, I'll call them compiled proofs. I don't think compiled is really the right word here. Then you don't have the scripts that generated those, then you can end up in a sort of arbitrarily difficult situation. Is this an issue in practice?
Yeah. So that's a very good point. So in languages that rely heavily on proof scripts, I do think that you should probably pay attention to those proof scripts. You should check them in and so on. I think that most likely for a language like Lean, you would want some kind of hybrid approach where you're keeping both the proof script and also somehow cache a proof object for it. One of the advantages of refactoring in Metamath is that it's very predictable what's going to break when you make a change. If you change the statement of a theorem, every single user of that theorem and nothing else will break. And you can load up the old version of the theorem, and then with the changed version of the theorem, there'll be a single line that's broken, and then oftentimes it will just be the same change that you just need to apply in each of these places, and then the refactor is finished. So I think it's a different approach to structuring proofs than you would see in say Lean, where you're pushing more heavily for those proof scripts. I mean, the proof scripts can be brittle in their own way, right? The proof scripts can also, if they break in the middle of some kind of simplification, it can be very difficult to figure out exactly how you need to manipulate the simp set in order to recover your old proof or something like that. So there are pros and cons, and that really I'm not saying that you should take all of these things. I'm saying that you should consider them and see how they interact with the mechanisms that you have in your own language.
Sure, fair enough. Thanks.
Okay. So I want to come back a little bit to this picture of the Metamath Proof Explorer. So this is a sequence of steps, and this is visible as an HTML web page. This allows readers to explore any Metamath proof in as much detail as they like. You have hyperlinks. You can click all the way down. You see every single step. And it's really useful for both learning the rules of the logic, like how do these things fit together, as well as learning how the proof works without any required background. So this is a very different way of like, this is not, you're not looking at a tactic script, which, you know, you need to know all of the tactics in order to understand that. Here it's like the only thing you need to understand is how substitution works in order to understand each of these individual steps. You can just click on any one of these theorems and then you can see, oh, that's how that piece comes together with these others. So some ways which I've borrowed ideas from this into other languages. So the hash explode command in Lean 3 will display any lean proof in that kind of style, where you see every single step, and the explode widget command is an extension of this to use the widgets framework, so that you can even like expand and click through like you would with the HTML version. And also the MM0docgen generates proofs in a pretty similar style by default. So another way that Metamath is doing things differently than a lot of the other proof assistants is basically to have a simple spec for the logical core. So the Metamath has a prose specification in the Metamath book. This is about 28 pages with lots of explanation and examples. There's really an emphasis on parsimony in the language. And so that is to say, like, there are few moving parts. There's only a couple of keywords, and there's really only one keyword for doing any particular thing. Yeah. And also the HTML documentation that you can find if you go to the Metamath website is full of pages and pages of introductory material, and they assume really no mathematical background. Like here, this is sort of a diagram of how does an individual step work, right? We just take this expression and then we substitute these things in for that expression in order to produce this one step. So if you can understand that, then you can understand everything on the web page. So a consequence of these two factors, that it's simple to the fact that there's few things in the language, the spec is easy to understand, and there's lots of documentation on it, means that there are many verifiers. There are 19 known verifiers written in all of these languages. And yes, Lean 4 is one of them. There's even a Turing machine verifier. I'm quite impressed with this work. So a Metamath verifier was actually used to improve on the best bound for the smallest unprovable in ZFC busy beaver number. So the idea here is that we're going to construct a Turing machine which enumerates proofs in ZFC, and when it finds false, then it will halt. So you can't prove that this thing halts in ZFC. So if you want to prove, you know, how small can we make this busy beaver number? Well, we need something that enumerates proofs, and it turns out that Metamath is just the thing. And so many of those verifiers are tiny. Some of them are even fast. After writing this, I started wondering, you know, to what extent there were some that are both. And I'm sure there is some kind of Pareto optimality thing going on here, but there are reasonably small, reasonably fast verifiers. There are also multiple proof assistants, and this is something that you don't see in many other languages. So rather than having like one proof assistant, which is the thing, there's a couple proof assistants. The main ones that are used are the MMPA. This is the Metamath proof assistant, which comes with Metamath exe, as well as MMJ2, which I showed you a picture of. And there's another one called Metamath Knife that's in development. And Metamath is also being used for machine learning. This is connected to having a simple spec, because if it's easy to write a verifier, you can write a verifier inside your machine learning feedback loop and have the machine learning setup like learn proofs. And so GPTF was one fairly recent example of this, and Holophrasm is an earlier attempt at doing proof search inside Metamath. And yeah. So the takeaways I want you to take from this is that really first write a spec for your language, please. For Coq and Isabel, the main spec is the code, and I'm not aware. I mean, someone should definitely correct me at this point, but I'm not aware of any external verifiers for Coq and Isabel. Um, for Lean, there are external verifiers, but there's not really a spec that like writes down what are all the rules. There is my master's thesis, which covers the rules of the logic, but not the rules of the algorithm. And it turns out that the algorithm is actually somewhat important for being able to check large-scale developments like Mathlib quickly. Holite does pretty well on this part, but it's still mostly you just use the kernel and the fact that the kernel is only like 300 lines or something like that, and then the code is the spec. So in Metamath 0, the spec was really the first thing that was written, and it's kept up to date and everything. The other thing is you want to support low-level proof translation, both import and export. A lot of systems, they support import, but they don't support export. So they're sort of, everything for me, nothing for you. So this is hard. No one's really performing well on this metric. Metamath does pretty well, not by doing anything in particular, but just by being simple. So since it's simple enough, you can write a verifier inside your proof assistant that understands Metamath proofs. And MM0 was designed for this from the start, and it supports import from Metamath and export to Hull and Lean right now. Yeah, so there's another point which I probably won't spend too long on, which is that Metamath uses a sort of simple form of first-order logic, which was discovered by Tarski, which eliminates the need for proper substitution. And that is to say that you only need to understand direct substitution, so like textual substitution, without regard for bound variables, except that sometimes when you apply a theorem, you have to check that two strings don't contain the same variables. It turns out that these two operations are very easy to check and also easy to cache in a certain way that allows you to do this in a provably linear time way. And this isn't like, oh, we make it linear time by making the proofs exponentially longer or anything like that. No, the proofs are comparable in size to, let's say, like a lean proof object, but they are linear time to check. Whereas like dependent type theory has its asymptotic complexity is something like the proof theoretic ordinal of dependent type theory, which is some absolutely gigantic number. Some gigantic countable ordinal, and then it's somewhere up in the fast growing hierarchy. It's really bad. Yeah, so it's good to know that this is possible, and Metamath and set.mm is a proof by construction that this actually does work at a large scale. I think the takeaways here are that we should simplify the logical constructs that the kernel needs to know about, and we should support mechanisms that allow the kernel to keep up with more advanced mathematics without having to add more computation into the kernel. So using theorems, not tactics. So MM0 uses a subset of first-order logic that's sort of compatible with both the first-order logic and the Metamath style interpretation, which means that it can be straightforwardly translated to both. And in fact, Metamath 0 is currently the easiest way to translate between Metamath and other first-order or higher-order logic or dependent type theory style approaches. It doubles down on this linear time proof property by using a more efficient binary proof format. It eliminates some of the excesses that are needed for term construction, and other things like that. So this linear time proof property is under, it's making fewer assumptions than the MetaMath version. Um, so Norm Miguel did a great service to the world by bringing MetaMath to us and showing that it's actually viable for proving mathematics in the large. Even if you never use MetaMath yourself, you should consider how architectural decisions can affect your CI process and the turnaround time. And I don't mean just by a little bit, I mean by orders of magnitude. The trustworthiness and replicability of language rules. And how tightly tied together the proof assistant and the kernel are. So this is, sometimes the design of the language makes it so that every time you add a proof assistant feature or there's a request by a user, it causes pressure on the kernel. It causes some desire for the kernel to need to encompass that and grow and get more complicated. And to my mind, this is the primary reason why the kernels of Cuck and Lean are as complex as they are, is because it's driven by this need for, like, the kernel does computation. I want it to do lots of computation to be able to do this kind of computation, and definitional equality is not something that can be extended. So instead, you just have to add it to the kernel, and sometimes you add bugs to the kernel, and people this has happened in Lean 4 in recent past. Like, you added things to the kernel in order to make it faster for good reason, but you're adding more surface area for bugs to appear. And other things that architectural decisions can affect how well the uninitiated can understand what's happening under the hood. This is something that I often see issues with. Like, if I jump into an Isabelle code base, can I understand this by myself without having to be, a student of to be honest, NIPCA or something? So I hope that Metamath Zero is going to bring a fresh light on some of these ideas, and to build a foundation, a way to show the correctness of the current generation and the next generation of interactive theorem provers. So that's my talk. And are there any questions?
Well, let's first thank Mario for a nice talk. And indeed, any questions or comments, please just shout out.
I could just say that you can export proof objects from Isabelle, and I think people are working on a verified external checker. I'm not really sure how that's going, but the main problem, as far as I'm aware, is just that these, nothing about Isabelle's architecture is designed to emit reasonably sized proof objects. So typically they just end up being extremely large. So if you try to do this for the entire whole library, then it just runs out of memory.
Yes. So I am somewhat familiar with the work on Isabelle proof terms. I think that there's some structural issues with the proof terms that make them sort of blow up in size faster than they would as far as the number of actual calls to the kernel. So I think that there's a way to make that a little bit closer to linear in the time that the kernel would take. I think right now it's not that. So I'm hoping that can be improved, but yeah, right now it's difficult. Someone raised their hand.
Yeah, Dan or Tanya?
Yeah, it's Dan. I was wondering about your comment before about when you were talking about the whole light kernel, you were saying that people take the code as being the spec. But it seems to me that it's a good feature of a spec if the spec is computer readable, for example, for doing automated translation, verification, et cetera. And it's just clear what it means if a spec is computer readable, which means a spec should be code, right?
I think the spec should definitely be code as well. I think that you can definitely, and I would say that the many verifiers approach really demonstrates this, is that, if you have a prose spec, people can read it and then you can have one or more code implementations of it. And if you don't find the prose spec readable enough, or you prefer to read code, you can look at any of the verifiers. So it's good to have an executable specification, sure, but it's also good to have a prose specification for people who read words.
Oh, those people. Oh, okay, thanks.
All right. Any other questions or comments?
I see a question on the Zulip, but I guess that's the same person who just asked.
I have a quick question.
Uh-huh.
Do you view MetaMask 0 as like an actual proof assistant that people will be doing proofs in, either for the MetaMask, either for the like the set M stuff, or like even other logics, or do you kind of always see it as kind of this external tool that used for like interfacing and checking? And
I didn't talk too much about the way that the MetaMath 0 is set up, but basically there's two components. There's as I mentioned, there's MetaMath 0, the verifier, and then there's the proof assistant called MetaMath 1, which is that has all the editor features and so on. At the moment, it's built in a style which, like, okay, 5 years from now, it might look something like Lean. Right now, it's usable enough for me to be able to prove, all the basic theorems that I need for. So I'm building a bunch of theorems in Peano arithmetic so that I can prove the correctness of the MM0 kernel. But in order to actually write proofs at some kind of scale, I need a proof assistant, because the MM0 proofs are not designed to be easy to write. They are designed to be easy to verify, and the easy to write part is all put in the proof assistant. So that's why I said that I think the separation is really what's important.